For Lab 5, I wanted to observe the motion of a jumper jumping from the world's largest rope swing, and in doing so, determine the parallel and perpendicular components of the net force acting on this person. To do this, I utilized Newton's second law, the momentum principle, energy principle to create a computational model of this pendulum-like motion. And in doing so, I determined the components of the net force increased as the person approached the lowest point in the swing's motion. So for this lab, I couldn't use Tracker to analyze the motion of the jumper, but I was able to draw information from the video, such as the length of the rope, the freefall drop, and the mass of the person, and use the energy principle in Newton's second law to determine the final velocity, tension force, and spring force, which I would use later in my code. Overall, I wanted to find the speed and tension force at the bottom of the motion, 90 degrees, and at 30 degrees from the center of motion. I applied the energy principle to find the final velocity, where delta E equals delta K plus delta UG. Because there is no work on the system, the delta E is also 0. K initial and U final both go to 0, leaving us with U initial equal to K final. I then plugged in all the initial conditions like the mass of the person and the freefall drop length to get 27.9 meters per second as the speed at the bottom of the arc. Next, I used the momentum principle in order to calculate the tension force at the bottom of the motion. Because there is no dp/dt parallel at the bottom of the motion, I was able to set Fnet equal to Fnet perpendicular. And plugging in the initial conditions once again, including the final velocity, to find the tension force as 1,825 newtons. Then I calculated the speed and tension force at 30 degrees. To do this, I once again utilized the energy principle, where only the initial kinetic energy equals 0. I then plugged in the initial conditions and found the final velocity to be 28 meters per second. Then I was able to compute the height above the ground at this angle to be about 9.17 meters using these equations. And ultimately, using all of this, I found the force tension to be about 1,500 newtons. Finally, I'm able to find the stretch of the spring force equation. I was able to plug in the tension forces I calculated before and set that equal to the spring constant, which I found online, times the S, the stretch. I then found the stretch at the bottom of the arc to be about 0.06 meters and at 30 degrees from the bottom to be 0.05 meters. Moving on to my code, overall I was able to combine parts of Labs 3, which displayed Fnet perpendicular and parallel for a star's motion orbiting a planet, and Lab 4, which created a model of the circular motion of a pendulum-weighted spring. So I used parts of each VPython script in order to display the parallel and perpendicular of the rope's arc motion. So first, I put down the system properties that we were given or found: the gravity, the ball's mass, L naught, the spring constant, delta T, and T. I then specified the spring force vector, where L is the ball's position, the spring position, and found S to be the magnitude of L minus L naught. I also put down V initial as 0, 0, 0 because the system does start off at rest. I also used P equals mv to get the initial momentum. Then going into the while loop, I found F grav and F spring to F net, which I then used to compute initial and final momentum vectors in order to update the position of the system. I then update the spring with the change in the system's position. Then I found Fnet parallel, Fnet perpendicular, and Fnet using this equation. And finally, I updated the system's time so that t is less than 20, a number given in the video for how long they swung. When the simulation runs, we can see that as the person approaches the bottom of the motion, the components of the change in momentum increase with the parallel component, the blue arrow, pointing forward along the person's motion as the velocity of the person increases, and the perpendicular component, the red arrow, points more towards the attachment point or origin in the direction of motion. As the person passes the bottom of the motion, the parallel, perpendicular, and net force decreases, and at the moment when the person passes, they flip to point opposite the person's motion. Now the velocity of the person is decreasing as it heads up and away from the bottom, and the direction of the net force always points towards the origin point. I believe why this occurs, where it increases as it approaches the bottom and then decreases as it moves away from this point, is because the stretch is greatest at the bottom of the arc than anywhere else as calculated before, thus making the spring force on the rope greater as it reaches the most stretch point of motion.